Hello students, in this session we will discuss analysis of statically determinate portal frames. We will solve a numerical to calculate shear force, bending moment and axial force of portal frame and will draw shear force diagram, bending moment diagram and axial force diagram. So let's start with numerical. Here is the figure of determinate portal frame and we need to analyze given portal frame and draw shear force, bending moment and axial force diagram. The given portal frame has total 3 members, member AB, BC and CD. Length of member AB and CD is 5 meter and length of member BC is 4 meter. The portal frame has 10 kN horizontal load which is acting at point B and 10 kN vertical load which is acting at point E at a distance 2 meter from point B in member BC. The portal frame has 2 supports, 1 hinge support and 1 roller support. The portal frame has hinge support at point A and roller support at point D. Now, as you know that hinge support always have 2 reactions, one in vertical direction and one in horizontal direction. So, in our case, we are assuming that reaction VA, which is vertical reaction at point A, is acting in upward direction and horizontal reaction at point A is acting in left hand side direction. Similarly, roller support always offer one vertical reaction and we are considering that reaction VD is acting in upward direction. So, let's discuss steps to solve numerical. The numerical can be solved in 5 steps. In step number 1, we will calculate reactions VA, VD and HA. In step number 2, we will draw free body diagram of each member of portal frame AB, BC and CD separately. In step number 3, we will calculate shear force in all 3 members of portal frame and draw shear force diagram. In step number 4, we will calculate bending moment in all 3 parts of portal frame and draw bending moment diagram. In step number 5, we will calculate axial force in all 3 members of portal frame and will draw axial force diagram. So, let's start with step number 1. So, in step number 1, we will calculate reactions VA, VD and HA. And for calculation of reaction, we need to apply 3 conditions of equilibrium, which is also known as equation of static equilibrium. Equation of static equilibriums are sigma m is equal to 0, sigma v is equal to 0 and sigma h is equal to 0. So, let's apply first equation, sigma ma is equal to 0. It means summation of all moments about point A is equal to 0. Now you know that moments are of 2 types, anticlockwise and clockwise. If we take anticlockwise moment as negative and clockwise moment as positive, then summation of anticlockwise moment and clockwise moment about point A is equal to 0. So, we can write down anticlockwise moment is equal to clockwise moment. Now, from this given figure, at point A, there are 2 reactions VA and HA and both reactions are passing from point A so that both reactions will not generate any moment about point A. Now, this 10 kN horizontal load, 10 kN vertical load and reaction VD will generate moment about point A. So let's start with reaction VD. We assume that reaction VD is acting in upward direction and the reaction will generate anti-clockwise movement about point A. And the moment of reaction Vd about point A is equal to Vd multiplied with distance 4 meter. The distance is a distance between line of action of reaction Vd and point A. So here we write that Vd is an anti-clockwise movement and it is Vd into 4. Now this 10 kilonewton horizontal load will generate clockwise movement about point A. And moment of this 10 kilonewton horizontal load about point A is equal to 10 kilonewton, which is load, and multiply with 5 meter distance, which is distance between line of action of this 10 kilonewton load and point A. Similarly, this 10 kilonewton vertical load is also generating clockwise movement about point A, and the moment will be 10 kilonewton, which is load, multiply with 2 meter, which is distance between line of action of this 10 kilonewton load and point A. So if we solve this, then we will get value of Vd is equal to 17.5 kilonewton. Here we are getting positive value of Vd, so we can say that our assumption is correct. Earlier we assumed that reaction Vd is acting in upward direction, and after solving by applying equation of static equilibrium, we get answer of Vd as positive, so our assumption is correct. Now let's apply second equation of equilibrium, which is sigma V is equal to 0. Means summation of all vertical forces is equal to 0. And vertical forces can be upward forces or downward forces. And summation of all upward forces and downward forces is equal to 0. So we can write down it as upward forces equal to downward forces. So here in given portal frame, there are total 3 vertical forces. This 10 kilonewton vertical load, reaction Va that we assume that it is acting in upward direction, and reaction Vd which is acting in upward direction. So we can write that Va plus Vd is equal to 10. Now we can say that Va is equal to 10 minus Vd. And value of Vd is 17.5 kilonewton. So we get answer of Va is equal to minus 7.5 kilonewton. Here we are getting answer of Va as negative. It means our assumption was wrong and reaction Va is acting in downward direction. Now let's apply third equation of equilibrium, which is sigma H is equal to 0. Now horizontal forces can be of two types, right hand side forces and left hand side forces, and we are taking summation of all horizontal forces is equal to 0. So we can write down that right hand side forces is equal to left hand side forces. So here in given portal frame, there are two horizontal forces. Reaction HA is, we are assuming that it is acting in left hand side direction, and the given horizontal load 10 kilonewton is acting in right hand side direction. So we can say that 10 is equal to HA and HA is equal to 10 kilonewton. Here we get positive answer. It means that our assumption was correct. Now let's move to step number 2. In step number 2, we will draw free body diagram of member AB, BC and CD. Here from the figure, reaction Va is acting in downward direction and magnitude of Va is 7.5 kilonewton. So in free body diagram of member AB, first of all, we will draw reaction Va at point A, which is acting in downward direction and of magnitude 7.5 kilonewton. And to balance this reaction of 7.5 kilonewton, we need to apply same magnitude load at point B, which is acting in opposite direction. It means at point A, reaction VA is acting in downward direction, and at point B, reaction VA is acting in upward direction, and magnitude of both will be same. Now you can see from the figure, at point A there is another horizontal reaction HA, and magnitude of HA is 10 kilonewton and it is acting in left hand side direction. And at point B there is one horizontal force of 10 kilonewton which is acting in right hand side direction. So both will balance each other. So this is the free body diagram of member AB. Now let's draw free body diagram of member BC. Now in member AB at point B, we apply 7.5 kilonewton upward force, and to balance this force we will apply 7.5 kilonewton downward force at point B of member BC. Ultimately, both the load will cancel out their effect because one load is acting in downward direction and other load is acting in upward direction, and magnitude of both the loads are same. Now you can see that at point D there is one reaction VD which is acting in upward direction and magnitude of VD is 17.5 kilonewton. To balance this reaction VD, we need to apply 17.5 kilonewton downward load at point C. And to balance this 17.5 kilonewton downward load, we need to apply 17.5 kilonewton upward load at point C. Now this 10 kilonewton reaction HA will generate clockwise moment about point B, and magnitude of that moment will be 10 kilonewton into 5, which is 50 kilonewton into meter. So here at point B of member BC, we will draw one clockwise moment of 50 kilonewton into meter, and to balance this moment, we will draw another moment of anti-clockwise direction of 50 kilonewton into meter magnitude in member AB at point B. So this is the free body diagram of each member individually. Now using this free body diagram, we will calculate shear force, bending moment and axial force. So let's move to step number 3. In step number 3, we will calculate shear force in each member AB, BC and CD, and we will draw shear force diagram. So let's start with member AB. This is free body diagram of member AB, and we need to calculate shear force at point A and point B of member AB. Here you can see that at point A there is one vertical load of 10 kilonewton. So at point A, shear force will be 10 kilonewton. For calculating shear force, we will consider upward forces as positive and downward forces as negative. Now, in between point A and B, there is no load. So shear force at point B is equal to 10 kilonewton. Now let's draw shear force diagram of member AB. So this is line AB. Now at point A, shear force is equal to 10. So we draw a line of 10 kilonewton from point A. Now between point A and B there is no load. So shear force diagram will be horizontal line. So here we are drawing this horizontal line till point B, and the shear force diagram will be closed because here at point B there is one reaction which is acting in downward direction. So this is shear force diagram of member AB. Now let's calculate shear force of member BC. So for member BC we need to calculate shear force at point B, at point E and at point C. So let's start with point B. At point B there is one downward force of 7.5 kN. So shear force at point B is equal to minus 7.5 because load is acting in downward direction. Now shear force at E is equal to this 7.5 kN downward load which is minus 7.5 and this 10 kN vertical load is also acting in downward direction. So we will consider it as negative, so minus 10. Therefore, shear force at point E is equal to minus 17.5. Now, between point E and C, there is no load. That's why shear force at C is equal to minus 7.5 kN, which will balance reaction VD, that is plus 17.5 kN. Now, let's draw shear force diagram of member BC. So at B, shear force is minus 7.5 kN. So we are marking 7.5 kN from point B. Now at point E, shear force is equal to minus 17.5. So if there is no load in between 2 points, then shear force diagram will be horizontal line. So we will start with 7.5 kN at point B to 7.5 kN at point E, and then we will move in a downward direction to 17.5 kN, which is shear force at point E. Now, between point E and C, there is no load, so we will get horizontal shear force diagram. So, at point E, we will start with 17.5 kN. We will draw horizontal line till point C, and then we will close shear force diagram at C. So this is shear force diagram at member BC, which is negative diagram. Now let's calculate shear force in member CD. Here in member CD, there is no vertical load. Therefore, in member CD, at point C and point D, both shear force is equal to 0 and there will be no shear force diagram for line CD. Now, let's move to step number 4. In step number 4, we will calculate bending moment in member AB, BC and CD, and then we will draw bending moment diagram. So, this is free body diagram of member AB, and we will start from member AB. So, at point A of member AB, bending moment will be 0. Now, at point B, this 10 kN load will generate clockwise moment. And while calculating bending moment, we will take all clockwise moment as positive and all anti-clockwise moment as negative. So, this 10 kN horizontal load at point A will generate 10 into 5 means 50 kN into meter moment at point B. So, MB is equal to plus 50 kN into meter. Now, let's draw bending moment diagram of member AB. So, this line representing member AB. Now, at point A, bending moment is 0 and at point B, bending moment is 50 and there is no load in between point A and B. So, bending moment line will be inclined straight line between point A, which is 0, to point B, which is 50. So we get positive bending moment diagram of member AB. Now let's calculate bending moment in member BC, and here is the free body diagram of member BC. We need to calculate bending moment at point B, point E and point C. So at point B, there will be 50 kN into meter clockwise movement. So here MB is equal to plus 50 kN into meter. Now let's calculate bending moment at point E. So at point E, again this 50 kN clockwise movement is there. So plus 50 minus reaction VA of 7.5 kN, which is acting in downward direction, will generate anti-clockwise moment about point E. And magnitude of that anti-clockwise moment will be equal to 7.5 kN, which is load, into distance 2 meter, which is distance between line of action of this reaction VA and point E. So total moment at point E is equal to plus 35 kN into meter. Let's calculate moment at point C. This clockwise 50 kN into meter moment, so we are write down here as plus 50 minus this downward reaction VA will generate anti-clockwise moment about point C, and magnitude of that moment is equal to 7.5 into distance between line of action of VA and point C, which is 4 meter. So here we write down minus 7.5 into 4. Now this 10 kN downward force will generate anti-clockwise moment about point C, which is equal to 10 into 2. So we get total moment at point C is equal to 0. Now let's draw bending moment diagram at member BC. So at B, bending moment is plus 50. So here we draw 50 magnitude line at point B. Now at point E, bending moment is plus 35, and at point C, bending moment is 0. Now in between point B and E there is no load, so we will get straight inclined line as a bending moment diagram. Similarly, between point E and C there is no load, so bending moment line will be straight inclined line. So this is bending moment diagram of member BC. Now in member CD, at point C and point D, both bending moment is equal to 0. So there will be no bending moment diagram in member CD. Now let's move to step number 5, which is our last step of solving numerical. In step number 5, we will calculate axial force in all 3 members, and we will draw axial force diagram. So here we start with member AB, and this is free body diagram of member AB. Now we need to calculate axial force at point A and at point B of member AB. So you can see in this free body diagram there is one axial force of 7.5 kN at point A, and there is one axial force of 7.5 kN at point B. Both forces are at outside direction. It means that it is pulling member AB. That's why it will create tension in member AB. That's why this load will be considered as tensile load, and we will take it as a positive force. So axial force at point A is equal to plus 7.5, and axial force at point B is equal to plus 7.5. and axial force at B is equal to plus 7.5 because there is no load in between point A and B. Now let's draw axial force diagram of point A and B. So at point A, axial force is plus 7.5 and there is no load in between point A and B. So at B, axial force is 7.5. So this is axial force diagram of member A. So let's calculate axial force in member BC. In member BC, there is no axial force. That's why at point B and point C of member BC, axial force is equal to 0 and there will be no axial force diagram for member BC. Now let's calculate axial force in member CD. Here is free body diagram of member CD. And in member CD, at both the point C and D, there is 17.5 kilonewton axial load is acting. The axial load 17.5 kilonewton is compressive in nature and we will take compressive axial load as negative. So axial force at point C is equal to minus 7.5 and axial force at point D is also minus 7.5. And here is axial force diagram of member CD, which is negative in nature because of compressive forces. So this is end of this session. Thank you.